Let me give you a few details on what I call parameters in ANOVA. What do I mean by that? Let's begin with, this is something that can be of practical importance when we're going to study outputs from various softwares giving us ANOVA results. So let me just touch on this. This is a bit subtle details, but nevertheless. Let us consider a simple one-way setting. One-way ANOVA with group 1, 2, and 3, or A, B, and C. Let us assume we have just 2 observations in each, and 3 equal 2. Let us assume we have observations 1 and 3, 3 and 5, 5 and 7, just to make a simple point here. Then, of course, the average in the first group is 2, the average in the second group is 4, the average in the third group is 6. And then there are actually 2 ways to express the one-way ANOVA model. The one which I did not, the most easy one actually is not the one I chose in my main lecture. The most easy one would be expressed like this, to say that I have an average in each group and then some normal distributed variability within each group. By this expression I would have, of course I should say, mu1, which would be then estimated by the average in group 1, which is a 2. I would have mu2, obviously directly corresponding to the average in group 2, and I have mu3 directly corresponding to the average in group 3, right? That would be a straightforward expression of everything. Now, in my, you could say that's model 1. Model 2, still for one-way ANOVA, and is the one that I used in my main lecture. I expressed it slightly differently. I expressed it by having a overall mu and then plus alpha I plus epsilon ij, and then with the same assumption. The point is that what now becomes, and then I would estimate mu hat by the overall average. That would be 4 on all of my data here, taking the average of all 6 data points. That would be 4. Then I would estimate y1 hat as y1 bar minus the overall average, which would then be 2 minus 4, that would be minus 2 for the first one, and then alpha 2 hat would be 4 minus 4, 0, and alpha 3 hat would be 6 minus 4, that would be 2. So in fact, I would, in a way, have over-specified or over-parameterized my situation by expressing my model. Actually, I have the model 2 here given by, you could say, 4 unknowns, but really, there are really only 3 pieces of information. And of course, mu I corresponds to mu plus alpha I. So this is just to say that why the heck are we then looking at this more complicated and somehow a bit, you could say, ridiculous way of why expressing 4 things when really there is only 3? Why not stick to the 3 specification? Well, the point is that this one, the model 2, which we use and which is used by most software, more easily generalizes to 2-way or even higher way type ANOVAs. That is the reason why we usually use this slightly more challenging way of expressing. This gives us a bit of challenge for our interpretation, actually. In fact, if we specified by 4 different numbers, there could actually be different ways of providing 4 numbers to tell the story about 3 pieces of information. I've gave you one version here. By this version, using what I call the natural, other people would call that sum contrast, because the sum of the alphas are 0 in this. So actually we have a restriction here to make this to make this give any sense. The restriction actually is that the sum of the alphas are 0 for this. So there are 4 pieces of information, but there's a restriction to link it to the fact that there is really only 3 in play. However, there could be different restrictions used in telling the story. And the challenge of this is not just a mathematical thing that we could forget everything about, because the softwares will all of them use the more general way of expressing such model. And different softwares will use different ways of telling the parameter story and different restrictions. So that is my reason for bringing it up, because it becomes very practical for us if we look into output from software. For instance, in R, let me have a look. Actually, I jump to R here. I show you, I have the gold, the example from the main lecture on the glass, the platinum, and the gold, the gravitation constants. Here's the ANOVA for that. And then I look at the coefficients. This is a feature of R, that you can look at the results for the individual groups. If you run this coefficient function, look at what R is telling us. R is telling us something which is called an intercept. Usually that's the mu. This is not the overall average of all the data, right? Let us see. The overall average of all the data here is something differently. What is the overall average of all the data? That would be, let me see. The overall average of all the data is 6.6724 actually. Not so different, but actually it's not the overall average. What it gives us instead here as the intercept is the mean of the glass. Actually, R is ordering the groups according to alphanumeric names of the groups. We have glass, we have, in Danish actually here, glass, guld, and platin, which is glass, gold, and platin. Glass comes first, gold comes next, and platin comes third in terms of alphanumeric order. Then it calls the first one for intercept, and then it gives as the second and third pieces of information, it gives us the difference between gold and glass, and it gives us the difference between platinum and glass. So that's the way R by default tells us the story, gives us the glass average, calling it intercept. Then it tells us that gold is this different from glass, and it tells us that platinum is this different from glass. So actually what R is telling us is the following, that if we look at R here, it would tell us that mu, which is then the intercept, would then be given as, in this case, it would, for this little example here, it would be 2. Then it would tell us that alpha 2, whatever name it uses, actually it won't even tell us alpha 1, because alpha 1 is set to 0. That is the restriction in R, actually, the mathematical restriction, making this match the 3 pieces of information. In R is the fact that the first level is set at 0, and the second one would then be the difference between the first and the second group. What is the difference between the first and the second group? That is 2. What is the difference between the first and the third group? That would be 4. This would be the R solution by default, not telling us 4, -2, 0, and 2. No, telling us 2, 2, and 4 with the underlying assumption that alpha 1 is set to 0. It's telling us the same story, but in a different way. We need to acknowledge that when we are to interpret some of the output from R, potentially. Now just to make a little, not that it's important for us in our course, but another big software used for statistical analysis, so-called SAS, Statistical Analysis System, would actually do the opposite. In SAS, they would instead, by default, put alpha 3 at 0. That's just the way it works in SAS. The default would be alpha 3 at 0, and then the intercept would be the average in the third group, so to say. And then the difference, alpha 1, would then be -4, since the first group is 4 less than the third group, and the second group would be 2 less than the third group. And then by restriction, by default in SAS, the third group would be called 0. But still, I gave you 3 different ways of telling the same story. It's not that the stories are different. We just need to acknowledge the fact that there are different ways of telling the story. This becomes important when interpreting results output from softwares, and especially when we move on to two-way and higher order ANOVAs. This understanding of how we parameterize linear models like this can be important also for practical use of this. Thank you.